I'm pleased, very pleased, to participate here in the entrepreneurship webinar series. And, typically I try to share my experience as an entrepreneur and as, having done my own startup and so on in different roles, not so much in these big webinars yet. I'm proud we have so many participants here. And I think one of the items in this webinar is that we focus on specific topics. So our topic today, which I've chosen as the title of my talk. How do I proceed? Next slide. Here we go. And this we can skip, of course. As you know, the title was from PhD to product development. So highlight, focusing on what skills do you have, what is your daily work as a PhD student in university or in some other research environment, and then how is that maybe different, and what will you expect if you really go into industry and be dealing with product development. And so as a quick agenda of this talk, I'll first, have one slide to introduce a bit more detail who I am, and then I will go through, the U²T story that, some of you might be too young to know, and because it was kind of an example of a technology startup in the photonics field, and I try to, pick many of my learnings also from the experience there, and then I will go through some of the items of the topic before we then can enter the discussion. So as Brandon already said, I'm a physicist by training. I studied in Darmstadt and in Berlin, and already did my diploma thesis at a Fraunhofer Institute, at that time on scanning Auger microscopy of X-ray mask features. I mean, I was fascinated by, how real modern physics is really used to create the microstructures in the electronic circuitries at that time. Then I was with Heinrich Hertz Institute for Nachrichtentechnik here in Berlin for some 10 years, where I developed waveguide integrated photodiodes on indium phosphide, and also introduced high electron mobility transistors into that platform and into that foundry. And then in 1998, myself, Günther Unterbersch, and Dirk Trommer, we started a spin-off called U²T Innovative Optoelectronic Components, GmbH, which means limited in the German environment here. And then I was kind of picking up the role as the CEO, taking care of, most of the not so purely technical tasks, and actually stayed in that position until we finally sold the company to Finisar. We had some, acquisitions in Germany, but also in the UK that we did to complete our business. And after, we sold to Finisar, I was a vice president and general manager of Finisar for 2 more years, and actually for 4 more years, sorry, with Finisar. And then in 2018, I realized, as 1% representing 1% of the company's revenue and being remote from California in Berlin, I couldn't have much entrepreneurial influence in this big corporation. So I started this consulting firm to, help young entrepreneurs with my expertise and mostly also experiences. So that's my quick background. I will now go through a little bit, and this is, a shortened version of what I have talked about, before, about, the U²T, starting, growing, and then try to take that as a kind of a as a model, as a role model for a technology startup, and learn from that. And that is, and typically you will see that throughout the presentation, I used some old slides from the U²T times, and which from old talks I gave before, and also have some new slides to summarize the findings. So our, initiative, our startup was triggered by the interest of the market we had. In the institute developed the fastest photodiodes that were available for this wavelength range at that point in time. And we then, received interest. We received interest, from colleague researchers and other, developers in our customers' sites. And so we decided, let's commercialize this photodiode technology, but let's do that under our own control and for our own benefit, and be in control of our own luck. And then we just went to, the business registration offices here in Germany and started to company. And then only after that we thought about, business plan and what are the right questions that we needed to answer. And, I think it's at the end, it was quite successful that, and we were very lucky that, we were supported by this institute. We had access to the IP. We could make use of the infrastructure, which is a pretty expensive infrastructure, semiconductor foundry. We also had kind of a safety net for ourselves. If we were on a leave, so if it wouldn't have worked out in the first year, then we probably would have been able to go back. And well, if we wanted, maybe that wasn't really a choice for us then. And finally, it was a very big, benefit for both parties. For us, it was very good to have a technology partner and a revenue stream. And we created a revenue stream for the fab, for the institute, and finally were the biggest customer they ever had from Heinrich Hertz Institute. So what was our differentiation? Because very clearly you need one unique selling product proposition, to be able to enter the market, because there is nobody waiting for new players, but you need to provide something that is not there yet, or which you can provide better than somebody else. In our case, it was a waveguide integrated photodiode, where we could integrate, where we could place the photo absorbing layer on top of a waveguide and then use evanescent field coupling of the optical field into the absorbing layer to kind of distribute the light along the length of the structure, and therefore utilize the length for the efficiency of the diode, but still have a very, thin layer which enables a very fast response. So this was in simple words, the innovation that we provided, a product innovation, and we made a product development out of that. And we started, with a 40 gig photodiode at that time, and here maybe this is still, it has a Finisar logo on it, but it was still the very same design as when we started. From today's perspective, I wouldn't say it was a product at that time. It was just, lab samples that we were able to package, and we were able to package not just one, but maybe 10. But we started selling it very early to the academic and research world. And then I think important for us was to be able to continue developing new products according to the market needs. The communications field in optical communications developed from 40 gig or from 10 gig to 40 gig. This was when we started. And then into DPSK receivers, dual polarization, dual phase shift keying. Then we had, for that we needed also 40 gig receivers, and including an amplifier, an electrical amplifier in the same package. Then we included the optical network, let's say, processing into the device. And then, the world turned coherent, and we had the first true 100 gig coherent receiver in 2010. And then, extended, 100 gig here means maybe a bandwidth of 50 gigahertz, but then we, did also the next step in speed and for 100 gigahertz for the detectors and so on. And then we actually did a lot of integration work under the roof of Finisar to really, kind of provide very compact integrated devices. How was that possible? With customers, engaging and collaborating with our customers was key to our success. We were lucky, we knew who they are. They were able to talk to us and find us, and then we really listened to them and tried to build exactly what they want. And that was even, if we engaged with one customer to do what he told us, the industry finally, was then well aligned enough, let's say, that they could, we could not only sell to this customer, but to the entire market. And that was, I think, one of the key takeaway messages for a spin-off company and for a startup. We had to survive, a downturn in the industry, and we had to focus on our strengths. We were able to combine fast optical components with very high-speed electrical interconnections. And that was kind of, unique at that time. And we stayed with these core skills and stayed with the 40 gig and 100 gig and very high speed applications, even though for some 5 years the world had turned back to 10 gig because of the communications bubble that burst in about the year 2000. So you can see we had quite a nice success with the first 40 gig wave, in particular with test and measurement companies. And then, there was a kind of a delay of about 5 years in the introduction of real 40 gig applications. And during that time, we were focusing on what we were good at, and we had the stamina to survive that. And then were able to supply into AT&T when they deployed their 40 gig network. And then, of course, after 40 gig era was over, we had to address the 100 gig area, and we also did that. Of course, it took longer than we thought, but at the end, it was quite successful. Here, is maybe just a slide. We were then able to identify that, Finisar was kind of missing this skill set of very high-speed receivers and photon detectors, and went into, and that was the main reason why they acquired us, because it was very clear they need this technology as well as tunable lasers for the coherent market space. Maybe the summary here of typically longer talk is, know and build on your strengths. Don't try to do what everybody else is already doing. Identify the right partners. Customers are very important. Without customers, it will be very difficult, to define a product. You need a partner on the technology side, like an institute who is really leading edge and is not just a Me-Too player in their technology as well. Suppliers are incredibly important because, as a starting business, you don't provide much return for them. They have to bet with you on your growth before you even can buy, a lot of parts from them. So they need to share your strategy. And of course, investors, have to share your vision and ideals in good times and in bad times. And we can address the question, at the end of the talk, how we survived. team members is, I think, the last point, but it's actually the most important point. We have to have the right team supporting you and sharing your dreams. So listen to your economic reason. I think that's also important. There was a time when, the more money you burn, and today is more or less similar, right? If the more money you can get for quantum, for AI, startups compete in their financial rounds of tens and hundreds of millions. But even if you have access to this amount of money, spend it very wisely at the end. You need every dollar you have, and just don't waste it. And of course, stamina is required, not just financially. And of course, you will still need some luck. So that is, maybe the quick run through the story of my startup, which has been quite some time ago. And now let's try and focus a bit more on the transfer between a PhD researcher and then what is required for industrial product development. So what are the goals? How are the goals defined? And I think in a PhD thesis, well, you or your professor, based on what you're interested in, on the research topic you're interested in, you just set the goal. And then you say, okay, let's figure out this new material system and, look at it. And important, to be successful, to get your PhD at the end is that you have actually contributed new knowledge to the field. If it's no new knowledge, then you don't get a PhD because that's the purpose of research. And to create this new knowledge, you have to dive very deeply into one specific topic, be it a technology topic, be it a theoretical topic, be it, just exploring some new material. And typically you define scientific assumption, what do we expect, what should happen based on the existing knowledge, and then prove it theoretically or experimentally. And this can take longer or shorter. So, and explore the boundaries of what is physically possible. What is the real limit? Can I get this new physics process to detect photons somehow? And maybe, yes, you find, oh, I have, even though it's out of the band gap, I can still detect the photons and get a detector and find a signal, even though maybe the efficiency is not very high, but you have explored that this is possible. And then you can, if you are maybe more on the engineering side, you can create a demonstrator that shows, a record speed or something like we did in the beginning. We had the first 50 gigahertz photodiode ever, which was a record achievement, and it was not a product yet. Even though we started the company with that. And then finally you publish your results and you get a recognition from the academic world, which is, very satisfying. I gave talks in our research results everywhere, and it's very satisfying, to get the recognition of your research colleagues and present your work and discuss your work at conferences. And whenever your result is available and finished, you just, go back into your little chamber, write it all together, and then apply for the title and hopefully get it. So hero experiment is the headline. On the other side, on product development, you have to define, as the goal is to develop a product that your customers need. You need to fill a gap at somebody who will be your customer. A need needs to be defined. And then you need to diligently analyze, is this really not just nice to have or is it maybe very important to have for this customer, but is it also capable to generate profit? Because that's the goal. You want to generate profit for your employer, for your company, or for your own company. And if it's just one customer that needs two pieces, and then they are satisfied, even though their need was very big, well, then they would have to pay you a lot of money, to run a business for that. But typically you have to do so you have to look at that in front, and then create a unique idea how you can satisfy the requirements of the application. And unique idea, points to USP. Without a USP, why should customers buy from you, and why should your product be better than anybody else's? And then, of course, instead of kind of a hero bandwidth achievement, you need to identify, of course, and then fulfill all of the characteristics of the product in each of the products that you ship, in each of the parts that you ship, including non-technical ones. So we look at that a bit more in the requirements section. But of course, it's totally different, if having 150 gigahertz detector with 0.01 amps per watt efficiency, when a typical detector which is half the speed has, I think, maybe 50 times the efficiency. So you need to, and then all of the samples, all of the wafer, all of the chips on the wafer have to fulfill all of the characteristics. And that means you need to be able to reproduce and to repeat these results, not just for the proof of the scientific content of it, but really with a high probability to make sure you have a high yield product, which of course is impacting the cost. And then make sure the product is reliable. This is important. And you have to hit the window of opportunity in the market. Be still the first to deliver the solution to your clients. So this was, again, an old slide from, somehow it updated actually the date here, but it's was a slide from, I think, 2010 or so, when we showed, to our customers that this is our strategy. We want to deliver with our customer bases, the next generation components, and then support next generation systems. So we had a very strong focus also on technology research, on technology development, and really, and I think this was a key success factor, as I mentioned earlier. But the focus is on what the customers need. So let's go back. That leads us directly to requirements. So what are the requirements for a PhD student? So I wouldn't say stole, but maybe I borrowed that from the website from the University of Queensland. Some common qualities of good PhD students. You have to be very curious. You need to love learning from books or from experiments. You have to have very good attention to detail, because the devil is always in the detail. Time management is important, and persistence. And this is kind of reminds me of one of my last slides. You need to be, you have to stay pushing through the challenges, and even though you have failures and pushbacks, and then still make sure you get to the result you wanted. And you have to collaborate with your group and with other academic partners. And this requires quite some resilience, because it can be frustrating from time to time. This is not too different from what you will experience when developing products. So for PhD students and PhD researchers who maybe want to start a company are well suited, to endure the pain of going through a product development. And then what we see here, the activities is analyzing literature, reporting, communicating, writing up results, attending group and department meetings. So this won't change much. This will be even more maybe. But key is also the documentation of the work, because in controlled development process. Each step and each decision and each measurement has to be well documented. And now, if you look at the requirements for a product, well, the product requirements are defined in a hierarchical way from top to bottom, and then in this so-called V model, because it looks like a V, obviously. So, and they have to be defined prior to starting the actual development work from user needs, which is which is up here, what are the user requirements? What does the user want to do with the product, and how does he want to apply it? Down to the final details of how do you implement the software if applicable, or how do you make the fiber chip coupling in our case, and how do you make sure that the customer can screw this device on his PCB, for example. And then, of course, once you have defined all the requirements, in every level of hierarchy, then you have to also think about, well, how do I check that this is actually met, this requirement? So for each step here, for each requirement here, you have to define a test to validate that what you have developed is really satisfying, the requirement that you have defined beforehand. And then, you go down here in the process, defining everything. You do really, actually do the detailed development work, and then you have to go through all level of tests. Test is the package up to scale? Are all the measurements correct? And can we really, make it functional? And finally, try out the product in the application and submit it to the environment that it will have to perform in. So this is really, the complex procedure of defining a product requirement. And this means, all parameters have to be specified, all technical parameters. I mean, here's only, I didn't, in the short time find a long, specification list of one of these rather simple devices. But as a kind of a short list, you have these parameters have to be defined. Which application do you address? Only in the C band, not in the L bands, not in the O band. So this has to be defined. And then, what are the other requirements? What type of bandwidth do you need? And then that doesn't say, okay, somehow I can interpret my measurement like, yes, we have something like 30 gigahertz here because 10 dB is not so bad. No, you have a very defined limitation both on the upper end of the curve, on the lower end of the curve, which defines your tunnel of acceptance, and that your product has to lie within that, and for all the measurements you can take. And you will have to define, a target specification, but also, minimum and maximum values that must not be exceeded. And how do you test it? Just data. I mean, this is not a final production test. This was kind of, from a running development program. So, at that time, we had data from 4 samples confirming the typical value is 23, dB of polarization extinction ratio, for example. And then this also has to be defined, how do you finally test it, and from how many devices? Operation conditions have to be defined. I didn't mention that yet. So, what temperature range is this product defined for? And temperature is a beast. It can change everything. And typically in a PhD, you see this, you don't care. You do it at cryogenic temperatures, and it works, and great. You have your scientific learning. Anyway, non-technical requirements are key. And the first one I mentioned here is cost and scalability. If you have the product ready and it performs, but no customer can afford it because it would be just prohibitive for his product, then this has to be taken into account from day one. How do I design my product to be at the right level of cost? And of course, we have to comply to industry standards like Telcordia standards and, for example, REACH and RoHS standards, which are in the world now, defining the materials that you must not use in a product, like lead-free solders and so on, but also other materials. And then you have all typical standards defined. And how can you design the product that you will be able to reduce the cost over lifetime? Because the price will go down in these typical technology markets, so we will have to be able to cope with that. And then this is just a reliability assessment chart. You need to be sure that your customer has a value and cannot just measure it once and then it doesn't work anymore. Reliability is key. And then you have well-defined set of measurements in a set of so many devices. I think it was 12 at least pieces or modules in each of these groups, and then you measure the different, you submit them to different stress factors like high temperature over life, operating life, high temperature storage, moisture, damp heat, and all these temperature cycling, which is a mechanical test, cooling it down to cryogenic temperatures and then heating it back up to 100 over a very short period of time. So to just see how is the mechanical integrity, then you let it fall, you give thermal shock. So you really have to make sure that the device will still work when the customer has used or even abused it. And then the same applies for the chip level things, but with a bigger sample size. Don't want to go too deep into that. And then I think the other aspect I want to come to now is this multidisciplinarity of the work. And I think I only have one slide here, and I want to talk a bit more about it if I have the time. So product design doesn't just mean you need to design your semiconductor physics to make sure, yes, you can achieve this physical effect at the desired speed. No, you have to also understand what your application needs, confirmation. This is examples for our case, communications and information theory. How much bandwidth do I need to support a certain bit rate or baud rate? Then optical design, how do I get the fiber into it, and how do I make sure that everything is nice and polished and I don't lose much in reflections or have adverse effects there? How will we be able to test it and not just submit it into the most expensive CERN experiment and to test if it functions, but to really test it for production in a repeatable, cheap way. And then RF design was very obvious here in our cases, but mechanics is really a point that is, you wouldn't spend so much time in your semiconductor physics PhD on. If you design a product, this is one of the most important elements. We had, if you look at reliability and returns from the field, many of the issues you incur is mechanics, be it different temperature coefficients, be it that a customer screws the device over a little edge and then it bends. So we've had all these cases, and then you have to really understand the mechanics and improve the mechanics of that. to make sure that the final product works. And the actual photodiode doesn't care really, but the product is really dependent on this. So now let's look a little bit on procedures. Yeah, to write a PhD dissertation, define the problem, choose how you want to do your research, you design your experiments, then execute your research, discuss the results, and maybe you have to go back and compare that with literature. So there is a procedure, that you have to cling to. And here, then, what is the proposal? What is your workflow? You ask your questions, how, why. Your methodology has to be defined. So you also have kind of this multidisciplinarity here when you want to define your research project. And then document all the important findings. And documentation is key. And many of the work items and skills are quite similar. And in the industrial product development process, actually, it's a bit more than just product development. It's a product lifecycle management, PLM, which is really, where product development is one part of that product lifecycle management. And this is actually, and I can't stress that enough, it's the most significant process for the success of the company. You have to define, firstly, what is the best business opportunity? You have the concept and the design, and you need to understand, well, what will be my return on invest? How do I solve it? Is this worth spending my development money and resource on? And if you bet on the wrong horse, then you might have used all your development forces and still will not have a successful business. And ensure you have the timeline. Talk to your customer. When do you really need it? When do you need samples? When do you need to qualify your product? When do you really need to scale up production? So ensure timely delivery to the customer is really important here. And then, of course, also this process is set up to prevent failures. And we will come back to that again. So, this product lifecycle management includes the concept and design phase, the actual development process, production and product launch. And then, of course, after you've sold your product part, you have to support it and service it. And, maybe in some parts, in our case, that was more or less, how to implement it in the system, how to control, how to bias the photodiodes. If we had failures in the field, to understand the failure mechanism and improve it. And then today, recycling is, of course, also a very important factor of how to manage the product lifecycle. And then there is this, stage gate process, and I put that first example here from the internet. Scope, it defines a business case, then design the product, build it, test it, and validate it, and then you can launch it. And then each of these, phases are gated by a certain set of criteria, that allows this process to go from this step to the next step, and so on. And then, you have to do certain activities in between to make sure, yes, for example, the business plan is still valid, even though I spent half a year on defining the business case and designing the idea of the product, is it still valid? And only then you would continue in working on the prototypes. And this is, some examples from my life experience. U2T, we did all this work to define the development process, with a project pre-phase where we had a concept study. Can we do that? We looked at the business case, and we created a set of documents that was mandatory at that stage to pass through a group of people, group of well-defined people to approve it before we could go to the next milestone and start the development, design to performance, and design to manufacture. And then once you have maybe gone through an iteration here and there. Then you can start with the new product introduction procedure to present it to customers before you then go into the scale up until there's no more need for it. And the same was true here for the Finisar process. And we, of course, in the acquisition phase, we had to match those two procedures. So in a bit more detail, we, of course, we had to do flow diagrams for all these procedures, who PFM is the gremium in the company, who was able to, decide and to check it, and if not, what do you do then? Yeah, repeat your planning, and then the entire project development process is to be well defined in the company, and with clear decision points and with clear decision criteria also, which have to be predefined. And then what are now, I mean, I've showed you a lot of the topics, and what are the priorities? And the first priority is, well, how many years will it take to finish your PhD? Well, sometimes it takes longer, sometimes it takes shorter. Well, at the end, the result counts. But in the product development, time to market is key. Time is money. Each product delay will be very costly. First of all, it will cost more development time and more development effort, and you will have to use more material to do another iteration, and more importantly, more of your, very important engineers, to do still work on the same product and not on the next one. And then you have to hit the window of opportunity. The first to the market wins the majority of the return, which you can see here in a very simple way. First to market has the screen, opportunity. Well, the late to the market only can generate much less of the revenue here. And there is, of course, models how you can calculate it. I don't want to go into that in any more detail, any more deeper. And I mean, what is also important, in most of the B2B cases, you are gating not only your product and your revenue, but your customers depend on you. They need your product to, build their system, for example, and which is much more valuable product to sell. So you really are kind of, gating a much bigger business. So time is really the key message, and I think it's also the main differentiation between doing a research project in a university, in an institute, in a European funded project or DARPA thing. Well, if you're a year late, great, but if you are here a year late, you are maybe bankrupt. And this is just highlighting also this reliability and security of supply is another priority. Your entire customer's castle is maybe built on your little yellow brick here, and if this breaks, the entire customer castle, falls down, and this will be costly for them. So, you have to you really have to take care about the reliability of your products and do some preventive risk analysis. And this has to be implemented in your company procedures. And there are industry proven test procedures how you can prove that your product is reliable and the customers of that industry will accept it. And in looking at preventive failure analysis, this FMEA method is something that many PhDs that I met have never heard of. You have to look at what can go wrong, how bad would it be, how often could it happen, what can we do about it, and what actions can we do to really prevent that failure from happening. And this is really a business management process where you really use, in our case, just an Excel sheet template, and you and theoretically think through all potential failures that could happen. If something happens here, what will be, and then you have to understand what is the effect. What happens if this failure occurs, and then how likely is it, and what could be the root cause of it. How do you control it? How do you detect it, first of all? And then, by the severance of this failure, by the probability, how, probable is it to occur, and how well can you find it before it really, leads to fatal effect? How's the detectivity? That defines altogether the multiplication of the risk priority number, and then depending on the risk priority number, you can prioritize all these potential risks, and then define actions, how you can work against it, how you can prevent it, how you can maybe improve the detectability, how you maybe the best is of course how you remove the root cause. And then you have to also define who is going to be in charge of that and by when does this action have to be taken. And then, you can reassess this failure mechanism. And that is, I think, one very important procedure. So in summary, industrial R&D versus academic research, the motivation is different. You will have to generate profit from competitive products as opposed to creating deeper knowledge in a specialized field. The performance in the desired application at the right cost, meeting all specifications at the same time is the target, as opposed to maybe one record value in one parameter or gaining more knowledge that something doesn't work. It's also can also be the result of a thesis. Obstacles are rather reliability, manufacturability issues, and not so much, that you don't know how to do it, how to solve it. Typically what you want to do and how you do it, and how you measure it. You have typically the instruments, test instruments available, but then reliability, manufacturability becomes key. Focus is here really a multidisciplinary understanding of the product in its application, and not so much to become the most knowledgeable specialist in the world, of this specific field of expertise. And your feedback, and that is something very positive. The first money customers pay into your bank account is, a much better recognition, not just financially, but also emotionally, rather than having, given a good talk in front of an OFC or another community. So with that, I want to close, my talk, and I want to go through for the discussion.